Yeah, we did, but let's go back and look at it. So we graphed this yesterday. So this is example 1 on the front of the first page, okay? But we kind of finished it right when the bell rang, so I will go back through. So we talked about the idea that the first thing we actually want to look out in the problem is the domain part of it, so like where it tells us which x's belong to which piece of the equation. So the first equation is graphed when x is less than or equal to 0, and the second one when x is greater than 0. That made 0 like the point where we switch from graphing one object to graphing a different object. So we saw one way to do that on the top of the page. Way number 1 was graph each piece completely on its own separately, highlight the part you know you need to use for your graph, and then put it together on one graph. That's one option of how to graph those. Right? Option 2, okay, as you get a little more used to the notation and what it means, we said I could come to the graph, and when I see that it switches at 0, basically, one thing is graphed when x is less than 0, one thing when it's more than 0, then I kind of know there's like this boundary. This is not part of my graph. This is just the thinking that's going on in my head. Sorry, I think that might be mine. Yes. It's not my husband or my child. Okay. So this is my boundary. And then I have to decide what's graphed on each side. So, okay, that's okay, yeah. So 3x plus 1 is graphed when x is less than or equal to 0. If it doesn't work, there's handheld ones over here, David. So I know when x is less than 0, on this side of the graph, I'm going to be graphing this line, okay? When it ends at 0 right here, is it going to have a closed point or an open point? So the 3x plus 1, that part of the graph, does it land actually on 0 like closed point, or is it going to have an open point at 0? Closed, because it says x is less than or equal to 0. So if I want to mark it for myself, I know this one's going to have a closed point on that boundary. This is just the thinking in my head, right? This isn't any of the graph. And then just as an idea so I know what's going on, what kind of figure is this graph going to be? A line. 3x plus 1, mx plus b style, okay, is a line. So I'm basically going to graph this equation on this side and end it with a closed line on the boundary, and it should look like some line with a positive slope, so something like that. On the other half of the graph, with the numbers bigger than 0, I'm graphing that other part of the equation, the x minus 2. Along the boundary, should it have an open point or a closed point? Open, because it says x is greater than 0, but it doesn't say x can equal 0. So when it ends at 0, it has to just have an open point on that boundary. What shape is x squared minus 2? A parabola, okay? So just so that I have an idea of what I'm doing, that's what's going on. So the line graph's going to go on this side. The parabola graph's going to go on this side. This is what their endpoints are going to look like on the boundary. Okay? Now I just have to kind of get them in the right place. Okay? So if you're not sure how to get them in the right place, graph them how you always would. So how would I graph a line normally? I would plot the y-intercept, and then I would use the slope to draw the rest of the line. Okay? So I would plot the y-intercept at 1, and then the slope is 3, like up 3 over 1. Okay, rise over run. I could go up 3 and over 1, but I've kind of just broken the rule of my function, okay? Because I don't really want to draw the line going this way, right? That crossed over the boundary, and the line's supposed to be on this side of the graph. So I'm just going to make some points in the other direction so I can draw the line in the direction that I want it to go. So instead of going up 3 over 1, another choice for me is to go down 3 over 1 and draw my line this way. Okay. And it's okay that I have the closed point on the boundary, because this graph is going to have the closed point on the boundary because it has the equal to at 0. Okay. All right, so this little extra point was something that I'm not going to fill in because I don't want to graph that line on this side. So now to draw this parabola, okay? So it's kind of like the parent. What's the only transformation that this quadratic has from just being x squared? It's down 2. So basically, it's the same parent parabola, but down 2. So instead of the vertex being at 0, 0, the vertex is going to be at 0, -2. Okay. Now that's right on the boundary. So am I going to draw that vertex as a closed point or an open point? This graph, open point. Okay, so I'm going to go ahead and mark that. It's an open point. And then because there's no stretches, compressions, reflections, that was it. This is the vertex. Should the parabola face up or down? Is there any negative in front of here? No, so it's going to go up. Are the points going to be the normal distances they are in the parent graph, the same distances, or are we going to stretch and compress it? So basically, is there any a value here multiplying x squared? No. So it's going to be the same thing as the parent function. So remember how the parent function for x squared normally has a vertex, and then 1 away is 1 up, 2 away is 4 up. Okay? And then there are mirror images on the other side. So we want to keep that same pattern of points because we didn't do any stretching or compressing. We just want to do it from this vertex instead of a vertex at 0, 0. Okay? So 1 over horizontally would be 1 above, so right there. I could mirror image it, but why am I not going to draw the mirror image point this time? Why am I not going to come on this side of the little dashed line that I drew and put the point over here for the parabola? Good, it crosses my boundary. The graph of x squared minus 2 would go over there, but in this equation, it's not allowed to go over there because it's only allowed to stay where x's are bigger than 0. So I can only graph the part of it from here, like the part you highlighted it on the graph yesterday. You would only be highlighting this part of it. And so then 2 away would be 4 up. So there would be my parabola part of it. Okay? And so you should see on your graph visually the pieces that you know exist. So I should see a line piece, and then I should see a quadratic or a parabola piece. Okay? So I see both of those things. This one? So it's like 2 away from the vertex, 4 above it. Like the same pattern the parent would have. Is that okay? So again, you don't have to do it like this. You could take each of those things, graph them separately, and then just highlight the piece you want to use like we did at the beginning and put it together. But after you've done a few of these, if there's a lot of pieces, it might be hard to graph them all separately. Once you get the hang of it, you might be able to do things that are a little bit faster. Alexis? This first one, so this is the vertex. So 1 away is 1 up, but 2 away is 4 up. Is that okay? Same pattern as the parent because of no stretch or compression. Okay? So this would be our piecewise graph for it, and that would be all. So what would the domain for this be? Is there any x's that you're not allowed to plug in? So 2 ways you can figure that out. You can actually look at the x values and the inequalities up in the function, and you can look at the graph and think about moving along the x-axis left and right. Is there any x value that if you pick that x value, you can't correspond to a point on the graph? No, right? I can pick this. That's my point. I can pick this. That's my point. If I pick something over here, it's on the line. Okay? But everywhere I go, every x value has some place it's going to end up on the graph. So the domain would still be all real numbers. And then you have to look at the range. Okay? So does the graph have a maximum? Does it hit a point that it doesn't go any further above? No. Okay? Does it have a minimum? No. Does it skip anything in the middle? Okay, so there appears to be a jump right here, right? So those y values from 1, 0, -1, -2, are they covered? Meaning like in this gap is -1, but are there points on this graph that have y coordinates of -1? Over here and over here. So because these overlap, even though there was a gap, the gap is kind of covered. There's still points within the gap on the graph, so the range would still be all real numbers. And then just so that you can understand that a little better, let me show you a situation where it wouldn't be. Say you still had something similar to this, but your parabola was like x squared plus 2 instead of x squared minus 2. So if this was your graph, the domain would still be all real numbers, but the range would be missing some piece in here. And so you would just list this part, and you would list this part. But there would be nothing listed for this range right here. Okay? This is different because there was a jump, but there was pieces of equations in between there that had points with those y values. Okay? Any questions about that? Okay, so let's look at on the back side, okay, example 2, the one at the top. Okay. All right, so first thing to ask yourself, how many pieces are in this piecewise function? 3, okay? What are the pivotal points? Where's the pivotal point or the pivotal points? Where is it going to kind of switch what I'm graphing? At what x values? 0. And even though there's 3 pieces, they just kind of all revolve around whether it's 0 or smaller than 0 or bigger than 0. Okay? So basically, again, my thinking process, this is not part of my graph. This is me trying to remind myself and not mess up and say, hey, when I get here, there's going to be some new stuff happening. Okay? What am I graphing on the left side of that boundary? What am I graphing over here? So do you guys agree with Hannah? So she's looking up here and she's saying that over there, I'm going to graph the absolute value of x. Okay? Because the absolute value of x is when x is less than 0. So on this side, I'm graphing the absolute value of x. Okay? When it gets to the boundary at 0, am I going to put a closed point or an open point on the boundary? Open, because it does not say in that first inequality that x can equal 0. So I'm just going to, you guys don't have to do all this, but this is just like so I don't forget. Okay? So open point. What does the second piece of the equation say? 3. Like, you don't plug anything in, you don't calculate anything, you just put points at 3. Okay? Where do we put points at 3 when x is what? 0, and only specifically 0. So literally, that second line of the equation is really 1 point on the graph, because it's saying only when x is exactly 0, you're going to put a point exactly at a height of 3. Nowhere else. Okay? And that's a solid point that's going to just be on the line at 0, 3. I didn't put it in the right spot right now. I'm just kind of doing my thinking process. Okay? So that's plotted on the boundary. Okay? Then after the boundary, when x is greater than 0, what am I graphing? X cubed, so a cubic. Okay? Notice they're pretty nice, like none of them have a lot of transformations. So you're basically just graphing pieces of the parent functions. Okay? And y equals x cubed, its point that's along this boundary at 0, open point or closed point? So look at x cubed. When it compares x to 0 on that line of the function, can it be equal to 0 or no? No. So open point for that function. Okay? All right, so if you have to off to the side, if you're like, I don't know how to put them all together, then what you would do is you would make yourself little pictures of what was going on. All right, so absolute value function, the parent graph normally looks like this. 0, 3 is just a point. I can deal with that. And then for a cubic, the graph normally looks like this. Don't confuse it with the cube root. Okay? One of them goes really fast upward, one of them goes really slow upward. Okay? All right. So for the y equals the absolute value of this, for this graph right here, my boundary is right here. I'm only graphing this equation on this side of the boundary. So basically, I don't want any of this. I just want this part of the graph. Okay? And I want it to end with an open point. That's what I said. So I'm going to put that on the graph. Okay? Open point at the vertex. Something like this. It looks like a line, but it is a piece of the absolute value graph. It happens to just be the piece that hasn't turned around yet. Okay? All right, on the boundary, I have the point 0, 3, so I'm going to go ahead and graph that. And then on the other side of the boundary, I'm graphing the cubic. So again, look at the cubic picture. The boundary's right here. We only want to graph it on that side of the boundary, so I don't want any of this. I just want this part of the graph. Okay? So I'm going to graph that. Open circle at 0, 0 again. Okay? Then point at 1, 1, and 2, 1, 2, 3, 4, 5, 6, 7, steep little curve in there. Okay? Is that all right with everybody? So again, you have the highlighting method, or you can do this. You can kind of just sketch each graph separately, think about which pieces. It's just like going through and highlighting and then putting them together on the graph. Okay? All right, domain. All real numbers, right? This continues to go to the left. This is really steep, but it will continue to move to the right also. It looks like we have a little gap here, but even though this point is missing here, when x is 0, we have a point that fills in for it right up here. So the domain is still all real numbers. And again, you could have seen that by looking at the x values up there. You're allowed to plug in x's less than 0. You're allowed to plug in x's that exactly equal 0 and x's that are more than 0. That covers every number on the number line. Okay? All right, what about range? Good job. So is there a maximum value that we reach? Is there a minimum value we reach? Yes, where at? 0. Okay? So it's definitely going to be y compared to 0. It's everything above. Should it be just greater than or greater? So we have a point at 0. Is it a closed-in point at 0? No. So do we ever actually reach 0? No. So just y is greater than 0. Okay. Is this all right? Yeah. Process it a little bit. Any questions about this one before you try another one? We'll let you start the other one by yourself, and then we'll check it. No questions? All right. Go ahead and try to graph this function. Pay attention to how many parts there are, where the boundaries are. There's more boundaries here than there was in the last one. If you look, it looks like both 0 and 4 are kind of some key numbers in my problem. So pay attention to that. Okay. My pieces should look like, what should the first piece look like? Part of a parabola. The second piece should look like that like square root shaped thing, right? And the third piece should look like a line. All right? So work with your group. See if you guys can figure out exactly which pieces go where, and then we'll check it. And okay, I'm going to put your answer up here quickly. Please check it. Okay, one comment about the line part of this, right before our drill starts. One comment about the line part. Here's the y-intercept, and here's the points that would result from using the slope. But the line does not start until x is bigger than or equal to 4, along this boundary right here. Okay? So I don't want to start the line until this point and then follow these. I don't want all these other points included because that was on the wrong side of the boundary. Okay? So this is what our final graph should look like. Parabola piece, square root piece, then it jumps up here, and we have our linear piece. Okay? The domain is still all numbers because you don't have any limit left and right. And the range, okay, there's no maximum. There's a minimum at 0. There's a gap right here, but that gap has points in another place on the graph, so we don't have to worry about that gap. So basically, points exist from 0 and above, so y would be greater than or equal to 0. Okay?